Welcome to my Lab 5. In this lab, I'll analyze and model the motion of Felix Baumgartner's space jump to show how a changing air density affects the motion of a falling object. In this lab, it was found that a greater air density results in greater drag acting on the object, causing the object to fall with lower velocity and reach its terminal velocity sooner. The two graphs here show these results, as the blue line represents an object falling through air of greater density than the red line, and it can be seen that the object represented by the blue line has a much lower velocity than the object represented by the red line, and it reaches a terminal velocity, whereas the red line does not. The physics involved in this lab revolve around Newton's second law, which states that an object's final velocity is equal to its initial velocity plus its acceleration times the change in time. The second equation shown here states that an object's final position is equal to its initial position plus its velocity times the change in time. A key assumption in this lab is that there are only two forces acting on Felix as he falls, a downward gravitational force and an upward drag force. The drag force can be calculated using a complicated equation which is shown here on the right. For the purposes of this lab, it's not necessary to explain this equation in great detail, but it is important to note that the air density through which the object is falling is a key component of this equation. Now we know from collected data about the jump that Felix jumped from a height of 39,000 meters. His mass was around 118 kilograms. His maximum velocity was 377 meters per second, and he reached this velocity after approximately 40 seconds. So now the next step is to take these initial conditions and the equations I explained on the previous slide and see if we can create a model in Python that recreates this situation. Here we can see the model I created in Python. Some key things to note about the model are, because Felix is jumping from the stratosphere, I've set g, the gravitational acceleration, to be 9.69, which is the correct calculated value, rather than 9.81, as it would be if you were closer to Earth. Also, r, the air density constant, has been set to an appropriate value for the stratosphere. This model calculates the force due to gravity as mass times the little g, 9.69, and it calculates the drag force using the equation shown earlier. It then calculates the net force as the gravitational force minus the drag force, and acceleration as the net force divided by the mass. Newton's second law is then used to predict the new velocity of the object, and the new position is predicted as well. When we run this code, we see that the model predicts a new velocity and position for Felix for each second that goes by. After 40 seconds, his velocity is 372 meters per second. We know that this model is successful because in real life, after 40 seconds, he had a velocity of 377 meters per second, which is close enough for the purposes of this lab. We now return to our model to predict the motion of Felix as he jumps from the atmosphere, which has a much greater air density than the stratosphere. To correct for this, all we have to do is change the value of g back to its normal 9.81, and because the stratosphere has an air density about 100 times less than the atmosphere, we correct the r value to 0.1 and run the model. This time we see that after 40 seconds, Felix only has a velocity of 111 meters per second as compared to 377 before. After plotting the results of our two model runs, these two graphs are produced. Again, the red line represents Felix falling through the stratosphere, which has a near negligible air density, and the blue line represents Felix falling through the atmosphere, which has a much greater air density. We see that when Felix was falling through the stratosphere, his velocity was much greater than when he was falling through the atmosphere, and in fact it was still increasing. When he was falling through the atmosphere, he reached a terminal velocity at around the 10-second mark and 50 meters per second, and continued to fall at that velocity for the remaining 30 seconds. Because of the much greater velocity, we can see that Felix fell a much greater distance when he was falling through the stratosphere than when he was falling at a lower velocity through the atmosphere. It should be noted that while these velocity values are positive, Felix is still moving in a downwards direction. He is simply just moving towards the Earth at these values. With these results in mind, we can answer a few questions. The first being, why didn't Felix reach terminal velocity before breaking the sound barrier? The answer to this question is because the air density is so low in the stratosphere, he experienced a near negligible drag force, which allowed him to continue to accelerate past the speed of sound. This continuous acceleration is shown here, as after 40 seconds he has still shown no signs of slowing down. The second question asks if Felix would have broken the sound barrier if he had jumped from the atmosphere. The answer to this question is clearly no, as when Felix fell through the much denser air of the atmosphere, he reached a terminal velocity after only about 10 seconds, and his speed was only 50 meters per second, which is not close to the speed of sound. Therefore, it is proven that as air density increases, drag increases, and terminal velocity decreases.